It's our last lesson of this unit. For our last lesson, we're going to revisit an older concept, area and perimeter. We're going to focus on all of the quadrilaterals that we've been learning about, and some of them should be familiar to you, but some of them might be new. So here we've got rectangles and squares, and I've represented the area and perimeter with various letters. B always stands for base, and H for height. In a moment, we're going to talk about what height really means, but for now, let's get all of the formulas written down. Some of our newer quadrilaterals, like rhombuses and kites, have additional ways that you can find their area. So you can use the base times the height formula for all of these because a rhombus is a type of parallelogram. But a rhombus is also a set of two triangles. And those triangles, you'll learn, are congruent. Therefore, you can also use this fancy formula for area, 1/2 diameter 1 times, diagonal 1 times diagonal 2. That is the only area formula we have for a kite. And I didn't include a perimeter formula here because you're just going to have to add the sides up. Or you can recall that a kite has two pairs of congruent sides, so really you only need to know two of the lengths and then just double them. Our last type of quadrilaterals are trapezoid. And trapezoids have a mid-segment that is the average of the two bases. So you can do the area in two different ways. You can either do 1/2 height times the sum of both bases added together, or you can do just height times the mid-segment length because it takes care of the whole 1/2 base 1 plus base 2. It is equal to that number. So before we move on and start trying to use these formulas, we need to know a little bit more about what we can and what we cannot use for B and H. The base can be pretty much any side as long as your height goes with it. So here I used the bottom side of each of these triangles, but technically it has to be the one that is perpendicular to the height. So I've labeled 4 triangles here, and all 4 of these triangles would have the exact same area, 1/2 base times height. Here we have an example where the altitude of the triangle is actually outside of the triangle. The black line represents the triangle itself, whereas the altitude has to be perpendicular to the opposite side. So we extend it out outside of the triangle to figure out how high up is that triangle, or what is the height of this triangle. A right triangle with the same height and base would have the exact same area. We can have an altitude that is close to the middle, or we can have an altitude that's close to the side of the triangle. As long as it's perpendicular to the base and it goes all the way to the next vertex across from it, it will count as the height. Now, triangles were sort of the easier version of this, which is why I brought them back, even though we're in quadrilaterals. Parallelograms, if you turn them on their side, you get the same type of problem. So I've shown 2 different ways that you can use the base and the height here. In red, we have a base of 16, which is the AB side of the parallelogram. And then from B to E is the altitude that would be used as the height for the parallelogram. Notice how they're perpendicular to each other. If I wanted to use the bottom segment, AD, I would have to extend out that line segment until I figured out how tall, or what is the height, from point C perpendicular to AF. That sounds kind of fancy, but really it's just they have to be perpendicular to each other. And we only need 2 of these. So as long as we have 2 sides, or a height and a base that are perpendicular to each other, we're good. Notice even though we had different numbers, they multiply out to the same value. So even though we had 16 times 9 versus 12 times 12, they both equal 144. Here we have a shape that's labeled with one of the diagonals labeled and one outside piece labeled. What shape is this? If you said kite, you are correct. There are two pairs of congruent sides, and they are not parallel. What formula would we use for the area of a kite? Well, you should have written this one down. It should be area equals 1/2 diameter 1, or diagonal 1, sorry, times diagonal 2. So we need to figure out how long are these diagonals. Here I've got one. 8 plus 12 is going to be our first diagonal, but I have no information about the other diagonal. I do remember, though, that the diagonal of a kite is bisected, only one of them. So if I know that this one isn't bisected, then I know that the other has to be bisected. So I only have to find one piece of this diagonal in order to find the full length of the diagonal. You also need to know that kites, their diagonals are perpendicular. All of this information is implied. This is where we go back to our definitions and we write down what is implied by this shape being a kite. Because they're perpendicular, I can use the Pythagorean theorem. I know that the two legs of the triangle are going to be 12 and some number that we're trying to find out, and that the hypotenuse across from the right angle is going to be 13. Well, if I solve that formula, we get that the height of that triangle is 5. And since that's half of the diagonal, I'm going to double it in my formula. So here we have 1/2 times diagonal 1, which is 5 plus another 5, times diagonal 2, which is the one that was labeled 12 plus 8. And we get a final value of 100 for our area. Before we move on, we're also going to cover a new idea, which is the polygon interior angle sum. Basically, no matter what polygon you're looking at, that's a closed shape that has straight sides, you can figure out the sum of all of the angles inside, even if you don't have all of the information, if you only know how many sides it has. So here I've shown a 4-sided polygon, a 5-sided polygon, and a 6-sided polygon. And you notice from one vertex, I've drawn lines, diagonals out to the opposite vertices, basically dividing it up into a series of triangles. All of those diagonals share one common point. Now, how does the number of sides of the polygon compare to the number of triangles that are created? You may notice that it follows a pattern. The number of triangles is always 2 fewer than the number of sides. So we can use what we know about triangles because all of the corners or angles of these triangles add up to make the wider angles of the quadrilateral or the pentagon or the hexagon. We can add up the angles of the triangles to get the angles of the shape as a whole. And our formula here is 180 times n minus 2, where n is the number of sides of the polygon. A regular polygon, or a regular n-gon, is a polygon that has sides that are congruent to each other. So for instance, this pentagon is a regular pentagon because all 5 sides are identical, are congruent. And as a result, all 5 of the angles are also congruent. So we can basically find the sum of all of the angles and then divide it by the number of angles that the shape has to figure out what each individual angle is equal to. All right, that's it for today. Lots of formulas. We're going to practice plugging in our numbers and solving in class.